positive semi-definite, in the real numbers, so everywhere basically. Okay, so let me write my formal definition of positive definite down now. It's probably pretty obvious what it is, but v of x and t is positive definite. D if v of 0 and t equals 0 for all t. And v of x and t is greater than 0 for all x not equal to 0, x and d for all t. And in the same way, we can write our definitions of negative semi-definite and negative definite just by flipping this sign around. So if I just wrote a less than instead of greater than, it'd just be negative definite. So I'm not going to bother writing it out, it's pretty obvious. Now in control systems, what we often see are quadratic forms. Now it's not any kind of requirement or something, it's just that they tend to be rather handy, easy to use. And basically it's what I'm going to stick with in this course. I'm not going to get into anything more advanced. So first of all, when I see something like this, the first thing I'm going to do is assume that Q is symmetric. And in the same way, I could always assume that something was 0 and 0, because I could just do a coordinate change. It's kind of a similar idea. I can always assume Q is symmetric, basically because I can make Q symmetric really easily. So we can assume Q is symmetric. In other words, the transpose of Q is equal to Q. If it isn't, we can make it symmetric. So it's kind of a trivial problem to make it symmetric. Just a little formula here. So suppose symmetric matrix QS exists. Such that when we have X transpose QSX equals X transpose QX, because QX, the original Q. So here QS is my symmetric one, Q is my non-symmetric one. And 2 Q transpose QSX equals X transpose QSX, because QS is symmetric. Then X transpose QS X equals 1/2 x transpose qs x plus 1/2 x transpose qs x equals 1/2 x transpose qs x plus 1/2 x transpose qs transpose x. But x transpose q x equals x transpose qx transpose, because they're both scalars. So the transpose of a scalar is a scalar. I get x transpose q transpose x. So therefore, x transpose qs x equals x transpose q transpose x. So I get x transpose qs x equals 1/2 x transpose qx plus 1/2 x transpose q transpose x. So I get x transpose q plus q transpose 2x. So I basically get a little formula here. Qs equals q plus q transpose over 2. So that's how I would translate a non-symmetric matrix Q into a symmetric matrix Qs. They're not the same matrix, but they do give exactly the same answer in terms of the scalar when you put them between x transpose and x. Okay, so they basically are equivalent as soon as you write them in a quadratic form. So we might as well use the symmetric one, because the symmetric one's going to be way easier to work with. So from now on, I'll just assume, whenever you see me write something like this, I'll just always assume the matrix is symmetric, and that's the reason why. Because I can easily make it symmetric. So my definition is Q is called positive definite. If x transpose qx is positive definite. Everyone have all this stuff? So another definition is that Q is called positive semi-definite. X transpose qx is positive semi-definite. And likewise, we can have negative definite and negative semi-definite q as well. And kind of the opposite way around. So an important thing to keep in mind when you do all these theorems is we're going to use this property a lot. So this is really something that's important for you to remember, is that if Q is symmetric and positive definite, then the minimum eigenvalue of Q times the norm of x squared is less than x transpose qx, which is less than the maximum eigenvalue of q times the norm of x squared. So I actually, Q doesn't have to be symmetric to write like an expression like this. Let's see if anyone remembers their linear algebra. So if Q wasn't symmetric and I wrote something like this, what would I use here instead of the minimum eigenvalue of Q? What would I use? If Q wasn't a symmetric matrix. Remember their linear algebra? Yeah, exactly. So there's something called singular value decomposition for non-symmetric matrices. And so you would use the minimum singular value here and the maximum singular value here. But it turns out there's all kinds of other difficulties for non-symmetric matrices, so it's not even worth it to do that. We'll just stick with the symmetric matrices. And there will be other advantages besides using eigenvalues as well. But anyway, just keep this equation in mind because we're going to use it quite a bit, so we should kind of remember where it came from. So L is a constant. And X transpose QX equals L, where X is just a 2x1 vector, and Q equals a symmetric matrix, 2x2 matrix. What kind of, what would you use to describe this equation in this case? What would it be? Anyone recognize that? Just talking about a 2-element vector, 2x2 symmetric matrix. What would that be? So if you just drew it, what would it look like? Does that help a little bit? So what is that?
Ellipse.
Yes. Who said that? Preston got that again? Oh, you got that too. Good. So is an equation of an ellipse. So that's what we're going to stick with in this course. We're going to stick with these ellipses. So there's these. We're going to stick with these quadratic forms and these ellipses. So there's not necessarily the only way to do it, but it's kind of a nice simple way, and a lot of people use it. So we'll just stick with it exclusively in this course, and you can always kind of visualize everything in terms of an ellipse, which makes things kind of nice. So just to remind you a little bit about ellipses. If b equals 0, the ellipse lines up with the x1 and x2 axes. So in other words, it might go this way, like horizontally. Each of that's the square root of L over C there, and that point is the square root of L over A there. And it looks like this if A is less than C. And then you get like a vertical looking ellipse. If A is greater than C. If A equals C, b equals 0, it is a
Circle.
circle. That's right. Excellent. With radius square root of L. But we're not going to see these in this course very often. So usually we'll have b not equal to 0. And when b is not equal to 0, there's some kind of rotation going on here. So the ellipses we'll deal with in this course will almost always look like that, because you'll rarely see the case where b is equal to 0. So almost always have some kind of rotation. So the ellipse will be kind of at an angle. So now I've given you enough information that we can appreciate this Lyapunov stability theorem. So if in the neighborhood D of equilibrium point x equals 0, there exists a continuously differentiable function b of x and t that maps D that maps D and positive real numbers for t into real numbers. If we have one condition that v of x and t is positive definite, so you can start to see where I'm getting here. So theoretically v could be anything that's positive definite, but what I'm going to use in this course is I'm always going to use something with an elliptical kind of quality to it. So it's actually going to be, each value of v is actually going to be a different ellipse. So you're going to get this kind of like bowl shape. But anyway, we're gonna stick with pretty straightforward functions when we do examples from now on. So theoretically, v can be anything that's positive definite, but in this course, I'm always going to use like one of these quadratic forms. So if you want to start thinking of it like that, it's basically a bowl. It's an elliptical shape. You can start thinking of it that right away. It might help you a little bit visualizing it. I'm going to write these things down. V dot of x and t is negative semi-definite in D. So if those two things are true, then the equilibrium point x equals 0 is stable. And in reality, I'm talking about something being locally stable. It's only in the case where D is Rn. In other words, it's negative semi-definite everywhere, then it is globally stable. worst case, there's negative semi-definite D, and then there's some region where it's going to be stable, like a local region. That region is not D, it's going to be smaller than D. So it's negative semi-definite D, so there's going to be some small region where it's stable. Unless D is like everywhere, basically. So if it's negative semi-definite everywhere, then it's globally stable everywhere. But usually we have a local result. Most commonly it's a local result. So there's going to be some region of stability around the origin, around x equals 0. So, but this theorem is nice to work with, very easy. Like I said, Vx of t is positive definite. We'll always use a quadratic form in this course. So when we do a positive definite V, we'll just have x transpose times some matrix times x. We'll do that every time. So you'll get used to seeing what I'm going to use for V in this course. This is the most common way to do it in control systems. It's very straightforward. And then all you have to do is either show V dot is negative semi-definite, but this is a control systems course. So really we're designing the control to ensure that V dot is negative semi-definite. So we're the control designers. We kind of have the power to design the control of anything we want. So we're kind of making this happen as in terms of control systems. Okay? But it's a lot easier to work with than the stability definition. So there's no epsilon and delta in this. It's very straightforward, very easy to work with. So let's do an example with some numbers so we can see how this works. So suppose I had x1 dot equals x2, x2 dot equals negative x2. So let's use a quadratic form for my V. And it's going to be important what the eigenvalues of this matrix are. So right now I'm not telling you how I get the numbers in this matrix. So I'm just, but it'll be obvious later on. We'll see how to easily calculate these numbers that we need for this kind of. But for now I'm just saying I'm going to prove stability using this matrix. And for now I have secret information on how to calculate that you don't have, but I will reveal that to you later on. So we have V equals 1/2 x1 squared minus 2x1 x2 plus 4x2 squared is positive definite. And V dot equals x1 times x1 dot minus x1 x2 dot minus x1 dot x2 plus 2x1 x2 dot. Sorry, 2x2 x2 dot. V dot equals x1 x2 minus x1 negative x2 minus x2 x2 plus 2x2 negative x2 equals negative 3x2 squared. Is this negative definite or negative semi-definite is the question. It's obviously, obviously I could write a less than 0 sign here except for when x2 is 0. So, it's not positive. So I know it's looking good so far. So I can probably, but I really, because negative definite is actually better than negative semi-definite. So for this case, what do you think? Is this a negative definite function or is this a negative semi-definite function? How many people say negative definite? You got one confident negative definite. How many people say negative semi-definite? Okay, it's 0. Oh, I got 2 negatives. Was that a negative semi-definite? I got 2 negative semi-definites and 1 negative definite. Everyone else is too chicken. But so we got negative semi-definite winning so far. So let's take a look here. So b dot of x1 equals 0 and x2 equals 0 is 0. B dot of x1 equals 1, x2 equals 0 would also be equal to 0. B dot of x1 equals actually absolutely anything, and x2 equals 0 equals 0. So now you can see that the definition of well, I guess the way I would put this is thus v dot of x equals 0 when x doesn't equal 0, the vector x doesn't equal 0. So all I can say is v dot of x is less than or equal to 0 or x not equal to 0. So v dot is negative semi-definite. So the important thing to look here is to see that all the states or variables that appeared in V also appear in V dot. So you can see that in V I have an x1 and an x2, but in V dot I only have an x2. I don't have that V1 anymore, so therefore it can't be negative definite according to my definition, because it actually has to be V dot equals 0 when the vector x equals 0. Which isn't true in this case. It's also 0 away from when vector x is not equal to 0. So I don't have both x1 and x2 in here. I just have x2, so it will be negative semi-definite, even though I can say less than 0, or less than equal to 0. Okay, so that's important to keep in mind. Anyway, because it's negative semi-definite, I can apply that theorem I just wrote on the board about Lyapunov stability, and I could conclude that the equilibrium point x equals 0 is indeed stable. Okay. So I want to write down, we'll take a break, but I want to write down my Lyapunov asymptotic stability first. So the theorem I just put up on the board was for Lyapunov stability, showing an equilibrium point is stable. But that's actually not very useful for control systems, because a stable control system is not a very high performance control system. Probably people wouldn't be happy with it. It'd be better if you had asymptotic stability, because asymptotic stability says the error is going to go to 0. So the error going to 0 is a very nice property in a control system, right? So let's just write down the theorem for Lyapunov asymptotic stability before we go for a break. I think we have 5 minutes or so that I can write this down. So there's one thing I have to define first, because there's one more thing that appears in this asymptotic stability definition. So v of x and t is decrescent in D if there exists positive definite v2 of x such that the magnitude of v of x and t is less than or equal to v2 of x. So as to draw that out, look like kind of talking about a three-dimensional thing here. I guess that's better get the norm of x. Okay? So, in other words, x, or v of x and t is actually bounded by this v2. So it's got to be in between these things. So it's, I mean, you can say this kind of bounded above and below by positive definite and negative definite function. If that makes sense. So the theorem goes, does everyone have this part here? So, well, there's two theorems. The first one is almost to the point, almost to the one I want. So the theorem for uniform stability is that under the same assumptions as before, if, in addition, we have v of x and t is decrescent, then x equals 0 is uniformly stable. And remember the difference between stable and uniformly stable in the definition was that uniformly didn't depend on the initial time t naught. I could calculate my delta without knowing what t naught was. So that brings us to the actual useful Lyapunov theorem that we can use in control systems. Is my Lyapunov asymptotic stability. So if in a neighborhood d